Alright, welcome back. In the previous page, we have mentioned how to construct a KD tree according to algorithm, right? And then next, we want to show how to do the query based on the KD tree to speed up a query process time. So in this page, we show you with the example. Let's assume we have constructed a KD tree already, and this KD tree also partitions the space into multiple regions, right? Recursively. And here we want to do a query, and we want to do query for the data points which are not inside this region, right? From here to here to here to here to here. Then how can we do this? Before, if we do the query, based on these ranges, it will be relatively difficult because we will have to compare all the data points one by one, right, according to the value we provided. However, here, if we have this KD tree, the query process will be much faster. Because we have partitioned the data region into multiple small regions already, in the query process, we can just follow the lines we draw in the vertical way and the horizontal way to find the target region, right? Here, this region is not in the right-hand side of this vertical line, right? If you still remember, this vertical line we denoted this L1 we drew before, right? This L1 corresponds to this node. In other words, this region we are querying for are in the right-hand side of this L1. Then we can go to the right-hand side of this branch, right? And we can ignore this left branch. We can go to the right branch, right? Okay, then we are in this node right now, and then we want to further check, is this region lying below this horizontal line or above the horizontal line? We see it is below the horizontal line, right? In other words, we can go to the left branch of the node. We can go to this node instead. We know this region should be below this node, right? Then we can further check if this region in the left-hand side of this vertical line or in the right-hand side. We see it is in the left-hand side, right? In other words, we can further query for the points which are one branch of this node. Because here inside this region we have some other lines, therefore we have multiple internal nodes here as denoted by these gray nodes. And according to these nodes, we can further find the data points which are not inside the region, right? Which will be the P7, P8, P9, and P10. And we can return these points as a result to the query. Alright, so in the previous page, we have introduced how to do the query already, right? And we show you with the example to do the query based on the KD tree to find some data points matching or within the range provided by us, right? And then here in this page, we want to show the formal algorithm we can use to do search inside the KD tree to query for some of the points which are not in the range provided by the queries. Okay, so as we can see, this algorithm is called search KD tree. It is also a recursive algorithm. In the algorithm, we have two inputs. The first input we have here is called V. This V denotes one node inside the KD tree. It can be either root node, or can be some leaf nodes, or can be some internal nodes. And this R denotes the data value range provided by a query, right? We have a query for some attributes. And so here we want to output all the data points at the leaf nodes below this V is nodes in the line in the range of this R. Then how can we do this? So in the algorithm, the first line we have is to check if this node V is a leaf node or not. Right. If this node V is a leaf node, then we can report this point stored in the leaf node because this node will be lying in the range of this R, right? And we can return these results as one part of the final results, right, for the query. Else, this else corresponds to this if, right? In other words, if this V is not a leaf node, it is an internal node, right? Then it will have both the left children nodes as well as right children nodes, right? So for the left children nodes, we can check if the region of the left children nodes of V is fully contained in this R range or not. This LC denotes left children. This V is a node of V, right? We mentioned here. This region denotes a region of the left children nodes of V. If this region is fully contained in this value range, if so, then we can report the whole subtree in the left children nodes, right? Because we can ensure all the points inside this left children nodes will be contained in this R. They should be returned as one part of the results, right? We can report it. Otherwise, this else corresponds to this if. If this left children nodes, this region is not fully contained in this R range. If so, then we can further check if the left children node, this region has an intersection with R or not, right? if the left children node in the region has some intersection with the R, then we can further do the search according to this search KT tree, this algorithm again. However, here we change this V nodes to the left children nodes of V instead. In other words, we recursively search according to the left branch of the tree of the nodes, and we can further do the check this process again, right, in the next recursive call. Okay, so this is about the left children nodes. And in a similar way, we can also check the right children nodes. These are sitting those right children of the node V, right? And we also check if the region is fully contained by the R or not. If so, we can report the whole subtree of the right children nodes. Otherwise, if there is an intersection of the right children nodes in the region with this value R, then we can further do the recursive call of the search KT tree right children nodes again. Okay, so this is a query algorithm we can do according to the KT tree we constructed before, which can speed up the query process or not, and it can also return all the results we want to query for.